Hello, we are in Chapter 3, Section 3.3, Arc Length and Curvature. And this particular section will talk about aspects of a curve that go a little bit beyond just their regular derivatives and integrals, but actually studying how the curve works, how it bends, what kind of frame we can use, and stuff like that. So let's get to it. In this video, we'll be focusing on the first objective, which is just the arc length. And then later on, we'll dive into the curvature and dive into these other things called the normal and binormal vectors. So we'll get to that. But for now, arc length. The arc length formula, if you look at it, is very similar to the arc length formula that we saw when we were studying parametric equations. When we were studying parametric equations, we took a look at the formula and we had the square root of x prime squared plus y prime squared. And we integrated that from the starting and ending point. Well, now, in general, if we're going to 3 dimensions, then we just add this third component, like a z prime. I know it says FGH in the notes, but it's essentially x prime squared plus y prime squared plus z prime squared. And what's interesting about that, I don't know if we actually were able to do this last time, but that is essentially the magnitude of the derivative. So it's as if we took this derivative, the derivative of r prime, so we get the derivative of r, and then we found the magnitude of that. And so that's how we get this nice compact formula for the arc length. And what's cool about this is that this works whether you look at it in 2 dimensions or 3 dimensions. Alright, let's do an example. Calculate the arc length of this parametrized curve. One thing to note is that this looks like a parametrized curve of a line, so it's actually a line. And so you can just put in 1 and 5 in there and then find the distance between the 2 points, because it's just going to be a straight line. But let's do it using our arc length formula, and to do that we would need to find the derivative, r prime of t. So r prime of t will equal to, this is just going to give us a constant 3, and then the second component will give us a constant 4. So the derivative of 3t plus 2 is going to be 3, the derivative of 4t plus 5 is going to be 4, and now we find the magnitude of that, magnitude of r prime of t, and that will equal to the square root of 3 squared plus 4 squared. So I believe this is going to be square root of 25, which is 5. So it's nice that it's a constant. It doesn't always end up being a constant, but it's nice that it's a constant. And so we do the integral, the arc length. We'll call it S for arc length, and that is going to be the integral from 1 to 5, because those are the limits that they give us, of r prime of t, which we found to be 5 dt. So a nice simple integral, 5t from 1 to 5. So we'll put 5 in there, and then we'll put 1 in there, and then we get 20. So the arc length here is going to be 20. Again, I want you to take the time and see if you can just put 1 and 5 into the vector valued function, and then you get 2 points. Find the distance between those 2 points and you should get 20. Alright, let's do another example, and this one's a 3-dimensional curve. So doing the same thing, the same kind of work. Let's find the derivative of r, get r prime of t. So this derivative will require a product rule because they have t times cosine t. So derivative of the first times the second plus the first times the derivative of the second. So this is negative sine t. I'm going to go ahead and just change this into a minus sign. So that's the first term. The second term is going to be 1 times sine t plus t times cosine t, derivative of first times second, plus the first times the derivative of the second, and then this last one is just going to be 2. Okay, that already looks kind of complicated, but let's go through it. We want to find the magnitude of r prime of t to see what we're going to put in the integral. So the magnitude is going to be the square root of cosine t minus t sine t squared. That's our first component. Plus the second component is sine t plus t cosine t quantity squared plus 2 squared. Okay, that looks like a big mess. Let's FOIL it out to see if we can simplify, and then we're gonna get the cosine squared t, and then this is gonna be a minus, and then we're gonna do twice the product of these two things, t cosine t sine t, and then the last term will be positive t squared sine squared t, and that's foiling out the first term. Now the second term will be sine squared t, and then again twice t sine t cosine t, and then the last term is going to be t squared cosine squared t, and then we have a 4 at the end. Alright, let's collect some stuff. Well, before we collect some stuff, let's notice that we have a positive and a negative of the same term. The middle terms of those two binomials will go away. We'll notice that the cosine t and the sine, or cosine squared t and sine squared t, make 1, and then we have t sine squared t and t squared sine squared t and t squared cosine squared t, and that makes a t squared times 1. And then so we'll simplify this triple underlined terms as t squared times parentheses sine squared plus cosine squared, which is 1. And then so this is the one that was all triple underlined, and then the double underlined here, these two terms make up 1, and then we add that to 4, so that makes a 5 plus 5, and I believe that's all the terms. So this is your r prime magnitude. Now we're going to integrate this from 0 to 2 pi, and then we're going to say t squared plus 5 dt. So it seems like a simple integral. It turns out that it's not that simple. You would need to do some sort of trig substitution, and then after trig substitution you'll involve some secants and all kinds of other functions and stuff like that. So let's just go ahead and take advantage of Wolfram or any integrating program that you have. So we're going to integrate from 0 to 2 pi the square root of t squared plus 5 dt, and then get our result. So I think if we were to do this by hand, I don't think we'll get necessarily the tan hyperbolic inverse that they got here, but if this is Wolfram's easiest route, then you can see it's not so easy to actually do the calculations by hand. So that's what generally happens with these arc lengths, because you're dealing with integrals of stuff with square roots, and those generally are not the easiest integrals to solve. So when we get our magnitude of the derivative to be a constant, that's usually always really nice and easy to integrate. But when we get some other more complicated things under a square root, not so easy anymore. Alright, so that is our first objective for this section, and yeah, good luck.